Another test we can use to decide if a series is convergent or divergent is called the direct comparison test. So we want to know something about some series, and we'll call the series we want to know A of n. Right? This is the one we're trying to decide something about. And we do happen to know something about a different series. The series we know stuff about is B of n. Right? So we could know for a fact that B of n converges, let's just say. And what's true is that B of n is always greater than A of n, or it's equal to, right? But B of n is bigger than A of n, right? So the series we want to know about is A of n. The series we know some things about is bigger than it. So it's kind of like the squeeze theorem. If we can compare A of n to a series that's bigger than it, and the bigger series converges, then we'll be able to conclude that the series involving A of n also converges. If a bigger series converges, then the smaller series must converge as well. Or your book talks about it in terms of being dominated by the series. So let's look at an example. The sum of our series from n equals 1 to infinity of 1 over 2 plus 3 to the n. We'd like to know what's going on with this thing. Does it converge or diverge? And we can compare it to this known series, n equals 1 to infinity, 1 over 3 to the n. Since the denominators are the same except for our original series, the denominator will always be 2 larger. This means that its overall value will always be smaller than 1 over 3 to the n. Now 1 over 3 to the n always converges because it's a geometric series. Now in case you can't see that, let's be a little more formal here, and I'll just rewrite it in another form. This is equivalent to 1 times 1/3 to the n power. Or if we want it in better form that you're used to seeing, this is also equivalent to 1/3 times 1/3 to the n minus 1. So this is a geometric series whose first term is 1/3 and whose common ratio is 1/3. R, in this case, is less than 1, so this geometric series converges. Now, by the direct comparison test, since this series, we'll call this series B of n, is always going to be bigger or equal to A of n, we know for a fact that the series we are talking about converges. This is a really nice test if you can see what you can compare to, but it isn't the kind of test that you want to spend a ton of time trying to figure out what should I compare it to. Right? At a certain point, you can either see that you can compare it and move on quickly, or you switch to a different test, generally speaking. Let's try another example. So the sum of the series that we are looking at from n equals, that's really huge, let me erase this. Let's try that again. The sum of the series from n equals 1 to infinity of 1 over 2 plus the square root of n. We'd like to know if this converges or diverges, and we'll attempt to use the direct comparison test. Now, in just like the previous problem, this is very similar to this example, 1 over the square root of n. And 1 over the square root of n can also be written as 1 over n to the 1/2. Now this is actually something that you should recognize. You may not yet, but this is an example of what's called a p-series. A p-series is any series whose rule is 1 over something to some exponent. 1 over x to r power. Right, and notice what, right, and r is going to be fixed, so some examples would be 1 over x squared, 1 over x, 1 over x to the 1/2, right? These are all examples of p-series. If you can see a p-series, if r is greater than 1, the series always converges. If r is less than or equal to 1, the series always diverges. So in our case, we're comparing it to a p-series that we know diverges. Let's see what happens here. If we were comparing it with these two things, 1 over n to the 1/2, that denominator will always be a little bit smaller than our original series, because our original series we're adding 2 in the denominator. So this means that in the same way as the previous problem, 1 over n to the 1/2 is going to be greater than or equal to 1 over 2 plus the square root of n. Now the problem is that we're comparing what we want to know to something we know, but the known thing diverges. And the direct comparison test doesn't tell us anything in that situation. In terms of divergence, it's actually the other way around. Right? So we said if a known series converges and it dominates the series we want to know about, then they both converge. If a known series diverges, so our known series we'll say is b of n, and our known series is always smaller than the one we want to know about, then they both diverge. This has those issues reversed, and so the direct comparison test with regards to 1 over n to the 1/2 is not helpful. We need to compare it to something else. So what about 1 over n? Right, 1 over n is a p-series. Because r is 1, we know that this diverges. And 1 over n, how is it related to 1 over 2 plus the square root of n? At first, it doesn't look like this is the case, right? Based on the first few terms of 1 over n, the terms are 1, when n is 2, you get 1/2, when n is 3, you get 1/3, when n is 4, you get 1/4, when n is 5, you get 1/5. And 1 over 2 plus n, its first term is 1/3, and then 1 over 2 plus root 2, and then 1 over 2 plus root 3, and then finally you get to 1/4. So it's only at the fourth terms when these two are equal, and then 1 over n gets smaller. And so this is a case where in the initial terms, this is not bigger, the 1 over 2 plus root n, but after a while it catches up and it ends up being bigger or equal to for the rest of the terms. And so this still meets the criteria. Eventually the sum surpasses it and is always smaller. So because n is greater than when n is greater than or equal to 4, this relationship is true, right? For pretty much everything is a way to think about it. This does meet our ability to compare directly, because what we want to know about dominates a known divergent series. So they both diverge. Right? We can conclude that our original series, I want to know about this, the sum of the series from n equals 1 to infinity of 1 over 2 plus the square root of n diverges by direct comparison with 1 over n. Again, the direct comparison test is useful if you can find a solution quickly, when you can figure out what to compare it to in a swift manner. Typically, this is a test that either I'm going to see how to use it if I'm using it on an exam, particularly the AP exam, and if I can't see swiftly, I'm going to move on to another test.